Hello YouTube. To the Moon, or Researching Flat Earth Part 3. It's not really flat Earth, but I've heard flat earthers say we couldn't talk to the moon because of the radio waves wouldn't reach there, or it's too far and there's too much loss. And let's talk about that using some 1960s technology. Is it even possible? And the big number that seems to really freak people out is the free space path loss. It's a spherical spreading loss. You can see the diagram here on the upper right hand corner, which kind of explains what's going on. As the sphere gets larger and larger, and if you have the same capture area, the power drops off by the inverse square. And there's the formulas down here in the bottom left hand side if you want to calculate it for yourself. But I'll save you the time because I did it. So this is the scale. This is how far the moon would be if the Earth were that small. So it's about 240,000 miles. So Apollo used a downlink frequency of 2276.5 megahertz, which is one of the frequencies they used. They used UHF and some other bands as well. So the path loss there is 211.3 dB, and that's huge. If you want to see that in power or in the ratio, you can see there's a whole bunch of zeros there down at the bottom. So you say, wow, that's a lot of loss. How's that possible? There's more to it than that. So if we take a look at this and say, let's take the path loss, and there's transmit power, some transmit gain, there's a receive gain because there's a big antenna on the Earth, and there's the receive sensitivity. So I took some estimates at the receive sensitivity, taking a thing called Boltzmann's constant, which defines the absolute minimum amount of power. I mean, the absolute lowest power that you can receive would be Boltzmann's constant. I prefer it in dB or dBm. So KTB in dBm is minus 198.6 dBm per Kelvin per Hertz. And then slow scan televisions like Apollo use 3 kilohertz bandwidth. But I used a much larger number, like 60 kilohertz. If I take 60 kilohertz, convert that to dB, I get 47 dB. Right, so that's kind of how that works. I used the full moon temperature, even though it may not have been a full moon when they were talking to the Apollo. But worst case, use the full moon, and that's only like 3 3/4 dB addition to the noise. So I threw in an extra 2 dB for losses and noise figure. I came up with a conservative 145 dBm, minus 145 dBm for the sensitivity of a cooled, cryogenically cooled receiver like you'd have at Goldstone. The antenna gain, quite simple. You can calculate this. This is courtesy of Microwaves 101, in case you ever want to check it out. But it's pi d over lambda squared. And the 10 times the log just turns that into decibels. So I get 22.3 dBi for the antenna on the lunar lander. And on the ground antenna, I get 60.5 dBi. And you can do this if you want. It's pretty simple. You can plug it into a calculator. So I did a link budget, and I come out with the margin of 36.6 dB, which is plenty good. And again, I used a wider bandwidth. The bandwidth I'm using is 60 kilohertz. They didn't need 60 kilohertz. They certainly didn't use 60 kilohertz for the TV. Audio, you don't need anything like that, right? I mean, that's absolutely insane. So it's not a problem. Absolutely no problem. In fact, if I were to take the lunar lander antenna and break it, and let's just say use a walkie-talkie, which has one of those little whips on it, which have about 0 dB a gain. Actually, it theoretically has 2, but never really has 2. But let's say 0, I'd still make a link to the moon. So they'd still be able to talk regardless, even if the antennas were broken. So how far is it to the moon? It takes light or radio waves 1.26 seconds to get to the moon from Earth. So, and we know the round trip path, right? So we get a distance of about 235,000 miles, which is pretty close. You need to know the time pretty accurately if you want to do this experiment. So anyway, that's my presentation. Go ahead and check out my math. Let me know if I did something wrong. I think it's okay. But if I did, let me know. Thanks for watching.